Any problems you'd like me to go over? Number 9. Yeah, well, I know why you had questions about this one because I don't think I talked about this stuff. Well, let me talk about it now, I guess.
So 1D particles in that? I think so. Number 9? I think you're on.
Oh, okay. Okay, you're right. You're right. Okay. One D. Okay, 1.5 meters high, 35 feet per second. Okay, so this rock, if this is the ground, it starts from a height of 1.5 meters and is thrown straight up. Its starting speed is 35 feet per second. And we want to figure out the highest point it reaches, how long does it take to hit the ground, the velocity just before it hits the ground, and then some displacements. Okay, excuse me. The first thing we have to do is get all the units the same. We have length units. This is number 9. We have length units of feet and meters. So I'm going to convert the feet to meters and do it in SI units. So 35 feet per second, 3.281 feet is 1 meter. And so this is about 10.67 meters per second. And first thing we want to figure out is how high it is at the highest point. I said that on free fall problems, I always choose my 0 to be at the lowest point in the problem. That's the ground in this case. And I choose my positive direction to be up. You have total freedom to choose those, but I think it does help to always do it the same way. It helps eliminate mistakes. And then I also have to choose an instant for time equals 0 and an instant for time final. Time equals 0 is going to be the instant that it's thrown. And we're choosing that because we're given information at that instant. So the information that we're given is going to help us with things like initial position, initial velocity. And then time final is going to be the instant it reaches the highest point because we're trying to calculate something there. So if you're trying to calculate something at an instant, you know that you have to make that instant one of your 2 choices. So this is the instant it reaches the highest point. And now that we've chosen those 4 things, we can figure out what variables we know and what variables we want. I'm going to just list them so we don't miss any. So time final, acceleration, P initial, P final, V initial, V final. Are we given how long it takes for the ball to reach the highest point? No. So I'm not going to write that anywhere. We're not looking for it. Acceleration. We know that anything in free fall or projectile motion has a downward acceleration of 9.81 meters per second squared. My positive is up, so that means downward is negative. So acceleration is negative 9.81 meters per second squared. P initial. Okay, well now we know that at time equals 0, this thing is 1.5 meters above the ground. 0 is the ground, and up is positive. So this is 1.5 meters in the positive direction from 0. So PI is 1.5 meters. PF, that's the position at time final. That's what we're trying to find, so I'm going to write that over here. V initial, now the velocity is always going to be the speed with a sign added on to tell you the direction. So I'll write this as, we know it's going to be plus or minus 10.67. And then we just have to think, is it moving in the positive or negative direction at time equals 0? Our positive is up. It's moving up, so this is going to be positive. And now finally, this is like the most exciting moment of any problem where you're calculating the highest point in a projectile projectile's travel. We know that when it reaches the highest point, the speed is 0. So velocity final is equal to 0. You know you're going to use that anytime you're calculating the highest point. All right, well, I think this equation will work. Let's check. PF has to be in it, and it is. And now let's go through the other things in the equation and make sure we know them all. A, we know. PI, we know. VF, we know. VI, we know, so this will work. So 2 times negative 9.81 times the quantity PF minus 1.5 is equal to 0 squared minus 10.67 squared. I'll multiply the 2 and the negative 9.8 first, so negative 19.62 times the quantity PF minus 1.5 is equal to negative 113.85. Now I'll divide both sides by negative 19.62. And we get PF minus 1.5 is equal to 5.80. And now add 1.5 to both sides, and you get 7.30 meters. Next, we want to calculate what's the elapsed time from when it's thrown to when it hits the ground. This is the first example that I've done in class where we have one part where we have a pair of choices for time equals 0 and time final, and then we have to change one of them for the next part, okay? So we can still use time equals 0 to be the instant that it's thrown. But now we're looking for information at the instant. You can think of it as the instant right before it hits the ground, or the instant it gets to ground level, assuming that the ground really wasn't there. We don't want to think of it as hitting the ground and stopping, because the instant it touches something, it's not in free fall anymore, and these equations don't work. So think of it one of those two ways, either the instant before it touches the ground, or think of the ground just being a height, and it's kind of as it passes through the ground on the way through, okay? Well, in order to calculate something when it reaches that ground level, we need to choose our time final to be the instant it hits the ground, or, reaches ground level. We can keep our 0 position and positive direction the same. So now let's go through this again and figure out what we know and what we want. We're trying to calculate what the stopwatch says at when it reaches ground level. So we're trying to calculate that value TF. Acceleration is still negative 9.81. P initial is still the same as it was, positive 1.5 meters. P final. Now, if we're looking for when the ball reaches ground level, the ground is 0, so our P final this time is going to be 0. V initial, like it was before, is 10.67. V final. Now this is why it's important that you recognize that we're just talking about this ball kind of reaching this height and not thinking about it actually hitting the ground. If you think about the ball actually hitting the ground, you might make the mistake of thinking that V final is 0 because the ground stops the ball. But it's not like that, because when the ground stops the ball, you're not in free fall anymore. You can't use the constant acceleration equation. So we don't know what V final is, okay? It has some downward velocity as it passes through that height. Okay, so what equation can we use? I think we can probably use this one. Let's double check. TF is in it, so that's good. And all the other things have to be known. PF known, PI known, VI known, A known, so this one will work. So 0 is equal to 1.5 plus 10.67 TF plus 1/2 times negative 9.81 times TF squared. And I'll rewrite this. 0 is equal to 1.5 plus 10.67 T minus 4.905 TF squared. Anybody know how we're going to solve this for T? Quadratic formula, exactly. So anytime you have, so notice that we're trying to find this variable. And in our equation, we have the variable squared. We have the variable, a linear term with the variable, and we have a constant. And anytime you have all three of those, the quadratic formula is the way to go, unless you want to try to factor it. But you don't want to try to factor it with these ugly decimals, you know. So I am going to ask my calculator to solve it. This is A, negative 4.905. This is B, and this is C. And the solution is going to be negative B plus or minus square root of B squared minus 4AC all over 2A. If you have a graphing calculator, a lot of these will do it for you. There's ways to, you know, so yeah, if you can figure out how to do that, it'll save you some time on problems like this. Also, if you have a graphing calculator that doesn't do it by itself, come talk to me in lab and I'll quick program it in. If you have like a TI-84, a TI-83 or something, it'll take me 1 minute or something to program in something that'll give you these answers, and then you never have to mess with it. So what I got here is negative 0.133 and 2.31. In this class, we are never dealing with negative times. So anytime you have an answer for time that's negative, that's all you need to know that you can eliminate that one, which means that our answer is 2.31 seconds. Any questions about that part of the problem? Okay, so now we want the velocity just before it hits the ground. Is there any reason to change our position equals 0, positive direction, time equals 0, or time final if we're trying to figure out the velocity at the instant it passes the height of the ground? No, there's not, because we're still trying to calculate something at one of the two instants we chose in part B. I think my lettering is actually wrong compared to the problem, but so our time equals 0 is still going to be the same, and our time final is still going to be the same. Do we know how long it takes to hit the ground? Well, yeah, we just calculated that. So time final is equal to 2.31 seconds. The acceleration is still negative 9.81. P initial is 1.5. P final is 0. V initial is 10.67. Bless you. And we're trying to calculate V final. So for this one, if you can ever use that velocity final equation, do it, because it's the simplest of the three. And we can use it here. So V final is equal to V initial plus ATF. And you can see it works because VF is in it and everything else in it is known. So V final is equal to 10.67 plus negative 9.81 times 2.31. And so V final is equal to negative 11.99 meters per second. Does it make sense that the velocity when it reaches ground level is negative? Yeah, because it's on the way down and our positive was up, so it's moving in the negative direction. Okay, now, I think probably now we're hitting the ones that, I forgot who asked the question, but these are probably the ones that were confusing. One of them is because I haven't mentioned the word displacement yet. So, okay, that's very legitimate confusion. So okay, so what's displacement? The displacement vector is the position vector at the, let's think of it as P final minus P initial. Okay, or you can think of it as the later position minus the earlier position. We are first trying to figure out the displacement from the point where the rock is thrown to the rock's highest point. So the displacement vector is going to be the position of those two. Which one is the later one? The position where the rock is thrown, or the position when it gets to the highest point? Yeah, so we're going to go the position at the highest point, which was the first thing we calculated, 7.30, minus the position when it's thrown, 1.5. And so we get an answer of 5.80. I wrote all these things with vector symbols over them. Don't worry about that yet. We'll get to that soon. So in one-dimensional motion, it's just this. That's just force of habit writing those symbols. Is everyone with me on that calculation of displacement? Okay, now what's the displacement from the rock's highest point to the ground? Which of those two is the later instant? Ground. So the position at the ground is 0. The position at the highest point is 7.30. And so the displacement this time is negative 7.30 meters. The sign of the displacement tells you overall what direction you have moved between those two instants. So going from where the ball is thrown to the highest point, its net motion, its overall motion is up in the positive direction. From the highest point to the ground, the net motion is in the negative direction down. Okay? And so now it asks us to draw some arrows in the direction of velocities and accelerations. So the first one is right after it's thrown. And we want to draw a velocity and an acceleration direction. Is it moving up or down? Up. So the velocity is the direction it's moving. So there's the velocity. Okay, there's two ways to think about the direction of acceleration. One is I said that the acceleration of gravity in free fall is always down, right? So you can think of it that way and draw that arrow right now. The other way to think about it is what happens is, does an object speed up or slow down when you throw it up into the air?
Slow down.
It slows down, right? Eventually it stops and comes back down. If it sped up, it would just keep going faster and faster until it disappeared. That would be weird. So if it's slowing down, what do you know about the directions of velocity and acceleration? Opposite, exactly. So if it's moving up, its velocity is up, and it's slowing down, its acceleration has to be down. Then it asks for the same two things when it reaches the ground level. At that time, is the ball moving up or down? Down, yep. So the velocity is that way this time. And again, there's two ways to think about it. The first one is the acceleration of gravity in free fall is always down at 9.81. So acceleration is still like that. The other way to think about it is if you drop something, it's speeding up on its way down, right? And so if it's speeding up and velocity is down, acceleration has to be down. Any questions about that one? And then Kay just asks basically for the wording that I just gave. If you think about speeding up and slowing down, once you figure out the velocity direction, you can determine based on what things do in projectile motion, what direction the acceleration is. If the thing's velocity is up and you know that it's slowing down, you know the acceleration is down. If the thing's velocity is down and you know it's speeding up as it goes down, then the acceleration has to be down too. Any questions about that problem? Any other problems you want to see? I mean, basically all I'm planning to do today is example problems and let you work on some example problems. So I'm as happy to do these as the problems I'm going to write up here. But, okay. Well, so now before I go on to the new stuff for today, I want to talk about the first exam and the first weekly assignment. So exam 1 is a week from today. So that must be 2/7. And the topics on the exam are everything that we've covered up through 1D particle kinematics. So, you know, on Monday, I suppose we'll probably talk about some new stuff beyond particle kinematics, but that won't be on the exam. Okay, so just kind of the stuff up through today. But remember that unit conversions, scientific notation, all that stuff you should be familiar with too, okay? So be sure that you look back at everything that we've covered and make sure that you remember it. I will always give all the equations that you need, so you don't have to remember any equations or conversions or anything like that. You don't have to remember any prefixes. I'll give you all that stuff. You just have to remember how to use those in calculations. Okay. And then the second thing is weekly assignment 1. Since we have the test next week, I gave you a lot of extra time to make sure. So if you just want to study until Wednesday, you'll have plenty of time to do this assignment after Wednesday. But if you want to start working on it now, it's there. And that is due, I believe that is Monday, 2/12. Okay. And just remember that you can feel free to talk to each other about this, work together on coming up with an approach for it. But then you need to be able to do this problem on your own. What you turn into me needs to be work that you've done on your own. Okay? So you can talk to people, figure out how to do it, but then you need to go and write it up and go through the steps and show me work that you've done on your own. Okay? Any questions about either of those? Okay. So here's the first example we're going to do today. I'm going to write this up here, and then we'll kind of step through it part by part. I'll give you time to work on it together. You can, compare answers, talk to each other about it, ask me questions if you get stuck, and then I'll go through it and you can compare your answer and your steps to what I did. It's just a way to sort of identify places where you might be getting tripped up, So let's say that a ball is thrown upward. From a height of 2 meters. With a speed of 15 meters per second. So first, calculate the greatest height the ball reaches. And second, calculate the velocity when the ball returns to a height of 2 meters. Okay. Well, let's just start out with part A. So take a few minutes, see if you can do part A, and then I'll do it. And then after I go through A, then we'll go on to part B. I'm going to start out by just sort of sketching what's happening in the problem. I think that can be helpful. So this is part A. It goes from a height of 2 meters. There's the ground. I'm going to put my 0 position on the ground and my positive direction up, just because that's what I'm used to always doing. And then I'm going to choose time equals 0 to be the instant that it's thrown. And time final is the instant it reaches the highest point. And now I'm going to list out what variables we know and what we're trying to find. Do we know time final? No, but we don't care. Do we know acceleration? We always know that in free fall. It's downward, which is negative for me. Do we know initial position? Yeah, that is positive 2 meters. P final is what we're trying to find. V initial, I think it said 15, right? So V initial is 15 meters per second, and you have to think about what direction it's moving. This is moving up, so that's the positive direction, the way I have it set up. And then V final, since it's reaching the highest point at time final, this is equal to 0. And so the equation that works is this one, 2a times quantity Pf minus Pi is equal to Vf squared minus Vi squared. So negative 19.62 times the quantity Pf minus 2 is equal to 0 squared minus 15 squared. So negative 19.62 times the quantity Pf minus 2 is equal to negative 225. Divide both sides by 19.62, negative 19.62. And you get Pf minus 2 is equal to 11.47. And then add 2 to both sides, and Pf is equal to 13.47 meters. Remember to put units on your final answers. By the way, if you're having trouble identifying from the wording of the question what information it's giving you, remember that any position stuff is going to have units of, well, length per time. If it's in SI units, it's going to have, no, that's wrong. It's going to, for position, it's going to have units of length. So if it's SI units, it's going to be units of meters. So anything in the problem that gives you meters or feet or whatever, that's telling you something about a position, okay? Velocity is always going to be length over time. In SI units, that's going to be meters per second. So when you look at a problem like this, you can see that 2 meters, you might not know right off the bat exactly what information that's telling you, but you can tell from the units that it's telling you something about a position, okay? You're going to use that information as a position in some way. Same thing with this. 15 meters per second means something in there is telling you about a velocity. And it's not always instant that you're just going to use that. Sometimes you need to think about the directions and stuff, but you know that that's velocity information. And then any acceleration is going to be units of meters per second squared. Okay, so now take a minute and see if you can work through part B. So now we're trying to figure out what the velocity of the ball is when it starts at 2 meters high, reaches the highest point, comes back down, and when it returns to that height of 2 meters. Anybody happen to know what the answer is? Just off the top of your head, like maybe in a physics class, you remember this or something? Okay. Well, it's going to be just an amazing surprise. You're going to love it. Just kidding. Yes. I mean, that's the acceleration. This is like an iconic one by Herbie Hancock. It's in lots of commercials and shows and stuff. This is Cantaloupe Island. It really grooves though. Want to hear something amazing? Do you know where Herbie Hancock went to college? Grinnell College in Iowa. Yeah. Okay, is there any reason that we have to change what we're calling time equals 0 or time final? In this one, we actually do, because we're trying to find information at a different instant than either one of our two from part A, okay? So our time equals 0, we can keep the same. That's the instant it's thrown or whatever I said, launched. But our time final now is gonna have to be the instant that it returns to that height of 2 meters. So we don't know the elapsed time. We don't know how long it takes to return. We do know the acceleration is negative 9.81. The initial position is the same as it was, 2 meters. The final position, this time is also 2 meters, even though it's traveled through this path, but it's returned to the same position it was at before. The initial velocity is 15 meters per second, and we're trying to calculate the final velocity. So we'll check this equation. I think this should be the one that works. 2a times the quantity pf minus pi is equal to vf squared minus vi squared. So we have negative 19.62 times the quantity, 2 minus 2 is equal to vf squared minus vi squared. And you can see 2 minus 2 is 0, so everything on this side goes away. You're multiplying negative 19.62 times 0. And so what this says is that vf squared is equal to vi squared. You know, vf squared minus vi squared is 0, so you can move one to the other side and you get this. So now take the square root of both sides. Oh, I didn't put in the number. Let me do that. Vi was 15. So this is 225. Now take the square root of both sides and you get that VF is equal to, and this is important, whenever you take the square root of a variable, remember that the answer can be positive or negative, okay? In math, usually you give your answer as a plus or a minus. In this class, we're always going to have a reason that one of these is the one we want and one is something else we don't want. So we have to think about what it means physically. So we get VF is equal to plus or minus 15 meters per second. Okay, so there are two answers for what the velocity could be when this thing is at a height of 2 meters. One is moving in the positive direction, and one is moving down in the negative direction. Which one are we talking about when it returns to that height? Yeah, so the answer is negative 15 meters per second. And this is actually a general fact in free fall and projectile motion problems. if you can ignore air resistance, then the speed on the way up is always exactly equal to the speed on the way down, just the directions are opposite. Okay? Which is why city mayors don't want you to shoot guns into the air on New Year's Eve, you know? I mean, if you shoot a gun, shoot a bullet, it has a lot of air resistance because it's moving really, really fast. But the basic principle is still the same. Like, you shoot it really fast, it goes up really high and comes down with somewhere in the ballpark of the same speed that it went up. And that is not good for things that it hits, you know what I mean? Okay, let's see, 20 minutes. Let's do one more. Let's see. So let's say that an object is thrown down towards the ground, launched down towards the ground from a height of 1 meter. And let's say that it takes 0.3 seconds until the object hits the ground or reaches the ground level. What's the velocity of the object when it's launched? Okay, see if you can work through that. So I already sketched out a little drawing of what's going on in the problem. I'm going to put my 0 position at the ground, positive up, so that means negative is down. My time equals 0 instant is going to be the instant that it's launched. And my time final instant is going to be when it reaches the ground level. This time we know what the stopwatch says when it reaches the ground. TF is equal to 0.3 seconds. The acceleration is always down at 9.81. P initial, if you start at 0 and like to get up to that point, you have to start at 0 and go in the positive direction 1 meter. So P initial is positive 1 meter. P final is where I put my 0 position, so this is equal to 0. We're trying to calculate the velocity at time 0, so V initial is what we're trying to find, and we don't know V final, but we don't care if we don't need to find it. Okay, so now we're looking for an equation that has VI in it and everything else in it is known. The one that should work is this one. PF is equal to PI plus VITF plus 1/2 ATF squared well, let's check and make sure. So it has VI, so that's good. And then the other stuff all has to be known. PF, yes. PI, yes. TF, yes. A, yes. So this one will work. So 0 is equal to 1 plus 0.3 times VI. Plus 1/2 times negative 9.81, that's negative 4.905 times TF squared. So I'll rewrite this as, minus 4.905 times 0.3 squared. We have 1 plus 0.3 VI minus 0.44. I'll leave it like that. Now we can, well, I can do it one by one. So add 0.44 to both sides. Now subtract 1 from both sides, and you get negative 0.56 is equal to 0.3 VI. Now divide both sides by 0.3, and you get that VI is equal to negative 1.87 meters per second. And does it make sense that that initial velocity is negative? Yeah, because it's being launched down, which is our negative. Any questions about that? Okay. Well, I think probably for at least some of Monday, we'll just keep going through some problems that are relevant for the test. Okay, that's it.